Math is supposed to have answers, right? But what if I told you that some math problems have been haunting the smartest minds for centuries, completely unsolved? In fact, some of these problems offer million-dollar rewards to anyone who can crack them. But why are they so impossible? Let's dive in. The Riemann hypothesis, the greatest unsolved mystery in mathematics. The Riemann hypothesis is one of the most famous and perplexing problems in mathematics. First proposed by the German mathematician Bernhard Riemann in 1859, it deals with the distribution of prime numbers, the fundamental building blocks of arithmetic. Despite more than 160 years of effort, no one has been able to prove or disprove it, making it one of the 7 Millennium Prize problems with a $1 million reward for its solution. Why is it so important? Prime numbers are at the heart of modern mathematics. They are numbers that cannot be divided evenly by any number other than 1 and themselves, e.g., 2, 3, 5, 7, 11. While these numbers appear simple, their distribution seems completely unpredictable. There is no clear formula to generate prime numbers in an orderly fashion. Riemann's hypothesis, however, suggests that there is a hidden pattern, a mathematical rhythm beneath the chaos. If true, the Riemann hypothesis would confirm that prime numbers follow a deep, underlying structure. This would have massive consequences for number theory, cryptography, and even physics. What does it actually say? At its core, the hypothesis revolves around a special mathematical function called the Riemann zeta function. Riemann proposed that all the non-trivial zeros of this function lie on a specific line in the complex number system, called the critical line. In simple terms, it means that prime numbers follow a pattern we have yet to fully understand. The consequences of a proof or disproof. If the hypothesis is proven true, it will revolutionize our understanding of prime numbers and make many long-standing mathematical theorems far more reliable. It would also secure modern encryption systems, which depend on the unpredictability of prime numbers. If false, it would send shockwaves through mathematics, forcing experts to rethink large portions of number theory and mathematical analysis. The search for the answer. Despite intense efforts from the greatest mathematical minds, no one has succeeded in proving or disproving Riemann's hypothesis. Powerful computers have checked billions of cases, and so far, they all fit the pattern. But a single counterexample could collapse the entire hypothesis. For now, the Riemann hypothesis remains a monumental unsolved mystery, tantalizing mathematicians with the promise of unlocking one of the greatest secrets in number theory. 2. The P versus NP problem, the greatest computer science mystery. The P versus NP problem is one of the biggest unsolved questions in mathematics and computer science. It asks a fundamental question. If we can quickly check whether an answer is correct, does that mean we can also find the answer quickly? At first glance, this may seem like a simple issue, but the implications are enormous. The answer could change everything from cybersecurity to artificial intelligence, and even how scientific breakthroughs happen. Understanding the problem. Mathematicians divide problems into 2 main types. P problems. These are problems that can be solved quickly. For example, sorting a list of names or finding the shortest route between 2 cities can be done efficiently. NP problems. These are problems where a solution is hard to find, but once we have it, we can check it quickly. A good example is solving a Sudoku puzzle. It might take hours to figure out the answer, but if someone hands you a completed puzzle, you can check if it is correct in seconds. The big question is, are these 2 types of problems actually the same? If every problem that is easy to check is also easy to solve, then P and NP are equal. This means that for every difficult problem, there must be an efficient way to find the answer. If there are some problems that can be checked quickly but cannot be solved quickly, then P and NP are not equal. This means that some problems are inherently difficult, no matter how powerful our computers become. Why does it matter? If it turns out that all difficult problems actually have fast solutions, then everything would change. Cryptography would become useless. The security behind banking, passwords, and online privacy relies on problems that are easy to check but hard to solve. If difficult problems suddenly became easy, encryption could be broken instantly. Artificial intelligence would advance at an extreme speed. Computers would be able to solve complex problems like drug discovery, protein folding, and scientific research in record time. Optimization problems would disappear. Tasks like scheduling airline flights, managing large supply chains, and designing efficient circuits would become effortless. On the other hand, if difficult problems remain hard to solve, it means there are limits to what computers can do, and some problems will always require massive amounts of time and resources. Where are we now? Despite years of research, no one has been able to prove whether difficult problems can always be solved quickly or not. Most experts believe that hard problems will always remain hard, but without a final proof, the question remains open. Solving this problem would not only win a $1 million prize, but it would also reshape our entire digital world. 3. The Collatz conjecture. The simple math problem that no one can solve. The Collatz conjecture is one of the simplest unsolved problems in mathematics, yet it has stumped mathematicians for nearly a century. The problem is easy to understand and requires nothing more than basic arithmetic, but no one has been able to prove why it works the way it does. It is sometimes called the 3x plus 1 problem, or the simplest impossible problem. The process starts with any positive whole number. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and add 1. Then repeat the process with the new number. The pattern continues, and according to the conjecture, no matter what number you start with, you will always eventually reach 1. While this has been tested for billions of numbers and always holds true, no one has been able to prove that it will always happen for every number. At first glance, the pattern seems chaotic. Some numbers decrease quickly, while others take many steps before reaching 1. For example, starting with the number 27 results in a long, unpredictable sequence before it finally settles at 1. The unpredictability of this sequence has led some mathematicians to compare it to random behavior, even though it follows strict mathematical rules. The mystery lies in proving that this pattern continues forever. Mathematicians have tried many approaches, but none have succeeded in showing that all numbers eventually reach 1. Some believe that a proof may require entirely new mathematical techniques that have not yet been discovered. Others think that a counterexample might exist, a number that never reaches 1, but no one has found one so far. The Collatz conjecture is more than just a curiosity. Similar patterns appear in various areas of mathematics, including number theory and computer science. Some researchers believe that understanding this problem could lead to new insights in these fields. Despite its simple rules, it remains one of the most frustrating and fascinating problems in mathematics. For now, the problem remains open. Whether the Collatz conjecture will eventually be proven or remain an eternal mystery is something only time will tell. 4. The twin prime conjecture. Are there infinite pairs of twin primes? Prime numbers are those that can only be divided by 1 and themselves, such as 2, 3, 5, and 7. Among these, there is a special category called twin primes, which are pairs of prime numbers that are only 2 numbers apart. Some examples include 3 and 5, 11 and 13, and 17 and 19. The twin prime conjecture asks a simple but unsolved question: Are there infinitely many such pairs? At first glance, it seems likely that twin primes should continue appearing forever, just like regular prime numbers. As numbers get larger, primes become less frequent, but they still appear. However, proving that twin primes never run out has been one of the most challenging problems in mathematics. Despite extensive numerical evidence suggesting that twin primes continue indefinitely, no one has been able to prove it for all numbers. One of the key reasons this problem is difficult is that prime numbers do not follow a simple pattern. They become more spread out as numbers increase, and mathematicians do not fully understand how they behave at extremely large values. Although various mathematical techniques suggest that twin primes should exist infinitely, no proof has been established. In recent years, progress has been made. In 2013, a breakthrough by the mathematician Yitang Zhang showed that there are infinitely many prime pairs that are at most 70 million numbers apart. This was a major step forward because it showed that some form of prime pairing continues infinitely, even if it was not yet narrowed down to twin primes specifically. Later work reduced this gap significantly, bringing it closer to 2, but the final proof remains elusive. The twin prime conjecture is important not just as an intellectual challenge, but also because it connects to deeper questions about the distribution of prime numbers. If proven, it could unlock new insights into number theory, a field that has direct applications in cryptography and computer security. For now, the mystery remains unsolved. Mathematicians continue to search for a proof, and while progress has been made, no one can yet say for certain whether twin primes truly go on forever. 5. The Goldbach conjecture. Can every even number be written as 2 primes? The Goldbach conjecture is one of the oldest and most famous unsolved problems in mathematics. It was first proposed in 1742 by the German mathematician Christian Goldbach in a letter to the legendary mathematician Leonhard Euler. The problem itself is incredibly simple to state. Every even number greater than 2 can be written as the sum of 2 prime numbers. For example, the number 4 can be written as 2 plus 2. The number 6 can be written as 3 plus 3. The number 10 can be written as 3 plus 7 or 5 plus 5. As numbers get larger, there are often multiple ways to express them as a sum of 2 primes. However, despite checking this pattern for billions of numbers, no one has been able to prove that it works for all even numbers. At first glance, it seems obvious that this rule should always hold. The larger a number gets, the more prime numbers exist that could be added together to form it. But proving that this works for every even number, no matter how large, has remained out of reach for mathematicians. Over the years, many partial results have been achieved. The problem has been tested by computers up to extremely large numbers, and no exceptions have been found. In 1937, the mathematician Ivan Vinogradov proved a weaker version of the conjecture, showing that every sufficiently large odd number can be written as the sum of 3 primes. This was an important step, but still did not fully resolve Goldbach's original statement. One of the reasons the problem is so difficult is that it deals with prime numbers, which are notoriously unpredictable. Unlike even or odd numbers, which follow simple patterns, prime numbers do not have an obvious structure. Understanding their behavior at an infinite scale is one of the greatest challenges in number theory. If the Goldbach conjecture is proven true, it would be a major breakthrough in mathematics, confirming a pattern that has held for nearly 3 centuries. If it is ever proven false, it would mean that somewhere among the infinite even numbers, there exists at least one that cannot be written as the sum of 2 primes. However, after hundreds of years, no one has found such an exception, and the mystery continues to fascinate mathematicians. 6. The Birch and Swinnerton-Dyer conjecture, the hidden patterns of elliptic curves. The Birch and Swinnerton-Dyer conjecture is one of the most complex and mysterious problems in modern mathematics. It deals with elliptic curves, which are special types of equations that play a key role in number theory and cryptography. Although elliptic curves might sound obscure, they are at the heart of some of the biggest advances in mathematics, including the proof of Fermat's last theorem. The conjecture tries to answer a fundamental question. How many rational solutions, or whole number solutions, does an elliptic curve have? Elliptic curves have been studied for centuries, but it was only in the 1960s that British mathematicians Brian Birch and Peter Swinnerton Dyer discovered a surprising connection between these curves and something called the L function, which is closely related to the Riemann hypothesis. Through extensive calculations, they noticed that the behavior of this function could predict whether an elliptic curve had infinitely many rational solutions or only a limited number. Their observations led to the famous conjecture that carries their names. The conjecture states that if the L function of an elliptic curve equals 0 at a certain point, then the curve has infinitely many rational solutions. If it does not equal 0, then the curve has only a finite number of solutions. While this might sound highly technical, it essentially provides a way to determine whether an equation has an infinite number of solutions just by examining a single mathematical function. The importance of this conjecture goes beyond theoretical curiosity. Elliptic curves have real-world applications in cryptography, particularly in the encryption methods used to protect financial transactions, communications, and even blockchain technology. A deeper understanding of elliptic curves could lead to advances in encryption and data security. Despite its significance, the Birch and Swinnerton Dyer conjecture remains unproven. Mathematicians have verified it for many specific cases, and modern computing has provided further evidence that the pattern holds, but a general proof remains out of reach. It is one of the 7 Millennium Prize problems, meaning anyone who provides a definitive proof will receive a $1 million reward. The quest to solve this problem continues to challenge the brightest mathematical minds. Whether it will be proven or remain an eternal mystery is a question that still lingers in the world of number theory. 7. The Hodge conjecture, unlocking the secrets of higher dimensions. The Hodge conjecture is one of the most profound unsolved problems in modern mathematics. It deals with the way geometric shapes behave in higher dimensions and aims to uncover hidden structures within them. While it is deeply connected to advanced mathematics, its core question is surprisingly simple. Can we describe certain geometric objects using algebra? At its heart, the conjecture is about algebraic geometry, which is the study of shapes that can be defined by equations. In everyday life, we are familiar with shapes like circles, squares, and spheres, which can all be described with simple equations. However, in higher dimensional spaces, these shapes become much more complicated. The Hodge conjecture proposes that even in these complex dimensions, the fundamental structures of these shapes can still be expressed using algebraic formulas. This conjecture was formulated by the Scottish mathematician William Valence Douglas Hodge in the mid-20th century. His idea was based on an earlier theory that classified different types of geometric surfaces. Hodge introduced a way to break down these surfaces into fundamental building blocks, and then proposed that all the key features of these shapes should be algebraic in nature. If true, this would mean that the geometry of complex spaces is far more predictable and structured than it appears. The implications of proving or disproving the Hodge conjecture go far beyond pure mathematics. Understanding the geometry of higher dimensional spaces plays a crucial role in physics, string theory, and even theoretical computer science. For example, many modern theories about the universe involve extra dimensions beyond the 3 we experience. If the Hodge conjecture is true, it could help scientists better understand these hidden dimensions. Despite its importance, no one has been able to prove or disprove it. Mathematicians have verified it for some special cases, but a general proof remains elusive. Like several other deep problems in mathematics, this conjecture has been designated as one of the 7 Millennium Prize problems, meaning that solving it comes with a $1 million reward. For now, the Hodge conjecture remains an open question. If proven, it would not only deepen our understanding of higher dimensional geometry, but could also open new doors in physics and beyond. 8. The Navier-Stokes existence and smoothness. Problem: the mystery of fluid motion. The Navier-Stokes existence and smoothness problem is one of the greatest unsolved puzzles in physics and mathematics. It concerns the equations that describe how fluids, such as air, water, and even gases, move. These equations are used in everything from weather prediction to designing airplanes. Yet there is a fundamental question that no one has been able to answer. Do these equations always behave in a predictable way, or can they break down into chaotic, unsolvable motion? The Navier-Stokes equations were first formulated in the 19th century and are considered the most important equations in fluid dynamics. They describe how velocity, pressure, temperature, and other properties of a fluid change over time. These equations work well in practice, and engineers and scientists use them every day. However, despite their success, mathematicians still do not know whether they always produce smooth and well-behaved solutions, or if, under certain conditions, they can lead to infinite turbulence or singularities. In simple terms, the problem is asking whether these equations always describe a predictable fluid motion, or if there are situations where they break down and no longer make sense. If a breakdown occurs, it could mean that certain extreme weather events or turbulence in aerodynamics might never be fully predictable. Solving this problem would have enormous implications for physics, engineering, and computer simulations. If it can be proven that the equations always behave well, it would confirm that our mathematical models of fluids are reliable in every situation. However, if it turns out that these equations can become chaotic under certain conditions, it could mean that there are limits to how well we can predict fluid behavior, which would affect everything from climate modeling to aircraft design. The Navier-Stokes problem is one of the 7 Millennium Prize problems, meaning that solving it comes with a $1 million reward. Despite its importance, no one has been able to provide a general proof. Some researchers believe that solving this problem might require entirely new mathematical techniques that have not yet been discovered. For now, the mystery remains. Whether the equations that govern the motion of fluids are always stable, or if they sometimes break down into complete unpredictability, is a question that continues to challenge mathematicians and physicists alike. 9. The existence of odd perfect numbers. A hidden pattern or an impossible dream. Perfect numbers have fascinated mathematicians for thousands of years. A perfect number is a number that is equal to the sum of its positive divisors, excluding itself. For example, the number 6 is perfect because its divisors, 1, 2, and 3, add up to 6. The next perfect number is 28, followed by 496, and so on. What makes this problem interesting is that every perfect number that has ever been discovered is even. Despite centuries of searching, no one has ever found a perfect number that is odd. The question remains, do odd perfect numbers exist, or do they simply not exist at all? The search for an odd perfect number has been ongoing since ancient times. The Greek mathematician Euclid studied perfect numbers over 2,000 years ago, and since then, mathematicians have developed many rules that an odd perfect number would have to follow if it exists. For example, it must be extremely large and have a very specific form. However, no one has been able to prove whether an odd perfect number must exist or whether it is completely impossible. If an odd perfect number does exist, it would likely be unimaginably large. Modern computers have checked numbers up to 10 to the power of 1,500, and still, no odd perfect number has been found. The lack of discovery suggests that perhaps they do not exist, But without a mathematical proof, there is no certainty. This problem is more than just a curiosity. Understanding the structure of perfect numbers could provide deeper insights into number theory, which plays an essential role in fields like cryptography and mathematical logic. The mystery remains unsolved, and until someone either finds an odd, perfect number or proves that they are impossible, it will continue to challenge mathematicians. For now, the existence of an odd, perfect number remains one of the great unanswered questions in mathematics. Will someone one day find one, or will it be proven that they simply cannot exist? Until 10. The Erdos discrepancy problem. Can we predict the randomness of numbers? The Erdos discrepancy problem is a seemingly simple question that challenges our understanding of number sequences. It was posed by the famous Hungarian mathematician Paul Erdos in 1932. The problem concerns infinite sequences of numbers and whether they exhibit predictable or random behavior. Specifically, it asks, given any infinite sequence of numbers, can we always find a predictable pattern within it? The basic idea of the problem is rooted in the concept of a sequence of numbers that can either be positive or negative. If the sequence is constructed in a particular way, following certain rules or algorithms, it may be possible to predict its behavior over time. But what happens when the sequence is randomly constructed? Is it possible that even in a random sequence, we can eventually predict a repetitive structure or some form of order? Erdős' conjecture focuses on sequences where the numbers are chosen according to certain conditions, and the question is whether there is always a way to identify a discrepancy that points to some hidden pattern or regularity. Essentially, Erdős suggested that no matter how you construct a sequence of numbers, there will always be a point where the numbers act in a regular way, even if the sequence appears to be completely random. The problem has puzzled mathematicians for decades, and while substantial progress has been made, no general solution has yet been found. Some researchers have used computational methods to study large numbers of sequences, trying to find evidence for the conjecture, but proving it across all possible sequences remains elusive. The Erdős discrepancy problem is part of a broader effort to understand randomness and order in mathematical structures. If solved, it would shed light on the deeper nature of numbers and how they can behave over time. It could also have practical applications in areas such as data science, where predicting patterns in seemingly random data is a crucial task. For now, the problem continues to challenge the mathematical community. If proven true, it could transform how we understand randomness in mathematics. If false, it would suggest that there are truly random sequences of numbers that cannot be predicted in any way. Next, ChatGPT said, 11. The Lycral numbers problem. The mystery of never-ending palindromes. The Lycral numbers problem is a strange and fascinating mystery in number theory. It revolves around a simple process that can turn any number into a palindrome, a number that reads the same forward and backward. The process is easy. Take any number, reverse its digits, and add it to itself. If the result is not a palindrome, repeat the process until you get one. For many numbers, this process quickly leads to a palindrome. For example, starting with the number 48. Reverse 48 to get 84. Add them together to get 132. Reverse 132 to get 231. Add them together to get 363, which is a palindrome. Most numbers eventually form a palindrome after a few steps. However, there are some numbers for which this process appears to never result in a palindrome. These numbers are called Lycral numbers, named after a term invented by Wade Van Landingham in 1969. The most famous example is the number 96. Despite being tested for thousands of steps, it has never produced a palindrome. Another famous case is 196, which has been tested by computers for millions of steps without reaching a palindrome. However, no one has been able to prove mathematically whether these numbers will never form a palindrome or if they simply take an extremely long time. The literal numbers problem remains open because proving that a number will never reach a palindrome is much harder than simply checking cases. Mathematicians suspect that some numbers may never become palindromes, but without a formal proof, the mystery remains. This problem is more than just a mathematical curiosity. It has links to chaos theory, computer science, and even cryptography, where understanding number patterns is crucial. Researchers continue to explore whether a general rule exists that determines which numbers will eventually become palindromes and which will not. For now, literal numbers remain one of the great unsolved puzzles of mathematics. Will someone one day find a proof that certain numbers will never become palindromes? Or will a hidden pattern emerge that finally solves the mystery? The answer is still unknown. 12. The density of coprime pairs. How often are two numbers truly independent? The density of coprime pairs is a fascinating unsolved problem in number theory that deals with how often two randomly chosen numbers have no common divisors except for one. Two numbers are called coprime, or relatively prime, if they do not share any common factors other than one. For example, the numbers 8 and 15 are coprime because their only common divisor is 1. However, 8 and 12 are not coprime because they share the factor 4. The central question of this problem is, what is the probability that two randomly chosen numbers will be coprime? While this may seem like a straightforward question, no one has been able to determine an exact answer that works for all numbers. Mathematicians have estimated the probability using advanced formulas, but a complete proof remains elusive. The best-known estimate for the probability is that two numbers chosen at random are coprime about 60% of the time. This estimate is closely connected to another famous mathematical constant called pi, which appears unexpectedly in problems related to number theory. However, proving that this estimate holds for all numbers is still an open problem. Understanding the distribution of coprime pairs is important because coprime numbers play a key role in encryption, modular arithmetic, and prime number theory. Many cryptographic systems, including those used to secure online banking and communications, rely on properties of coprime numbers to function correctly. A deeper understanding of their distribution could lead to improvements in these systems. Despite extensive research, mathematicians have yet to prove the exact probability of two numbers being coprime in a general sense. Some believe that the answer is hidden within the distribution of prime numbers, while others suspect that new mathematical tools will be required to solve the problem. For now, the density of coprime pairs remains an open question. Whether a final proof will emerge, or if this problem will continue to challenge mathematicians is still uncertain. But one thing is clear, solving it would unlock deeper insights into the fundamental structure of numbers. 13. The Capricar's constant mystery. A mathematical loop with no explanation. Capricar's constant is a strange and mysterious number that emerges from a simple process discovered by the Indian mathematician Dattatreya Ramchandra Capricar in 1949. It involves taking any four-digit number, applying a specific set of steps, and always arriving at the same final number. This phenomenon has fascinated mathematicians for decades, but no one fully understands why it happens. The process begins by choosing any four-digit number, with the condition that all four digits are not the same. Once the number is selected, the digits are rearranged to create two different numbers, one with the digits in descending order and the other with the digits in ascending order. The smaller number is then subtracted from the larger one. The result is a new four-digit number, and the same process is repeated. No matter which number is chosen at the start, after several steps, the sequence will always lead to the number 6174. Once this number is reached, the process continues to repeat itself indefinitely. Mathematicians have tested every possible four-digit number and confirmed that this rule holds without exception. The number 6174 acts as a kind of mathematical trap, pulling all numbers toward it in at most 7 steps. This strange behavior is why it is called Kapurkar's constant. Despite its predictable pattern, the deeper reason behind why this happens remains unknown. Mathematicians have analyzed the properties of this process and found that similar patterns exist in different numerical systems, but a complete explanation has yet to be discovered. Some believe that the answer may lie in hidden structures within number theory, while others think it could reveal deeper properties of arithmetic itself. Kapurkar's constant is a perfect example of how simple mathematical rules can lead to unexpected and mysterious results. While the steps of the process are easy to follow, the underlying reason for why this number behaves this way is still an open question. Will someone one day uncover the true explanation, or will it remain one of the strangest unsolved puzzles in mathematics? The answer is still unknown. 14. The Legendre's conjecture. Is there always a prime between squares? The Legendre's conjecture is a simple yet unsolved problem in number theory that deals with the distribution of prime numbers. It was first proposed by the French mathematician Adrien-Marie Legendre in the early 19th century. The question is straightforward. Is there always at least one prime number between any 2 consecutive perfect squares? A perfect square is a number that results from multiplying an integer by itself. Examples include 4, which is the square of 2, 9, which is the square of 3, and 16, which is the square of 4. Legendre's conjecture suggests that if you take any perfect square and its next larger perfect square, there will always be at least one prime number between them. For small numbers, this pattern appears to hold. Between 4 and 9, the number 5 and the number 7 are prime. Between 9 and 16, the number 11 and the number 13 are prime. Between 16 and 25, the number 17, the number 19, and the number 23 are prime. Even for much larger numbers, computers have checked and found that a prime number always exists between consecutive squares. However, despite testing billions of cases, no one has been able to prove that this pattern continues forever. The challenge lies in the unpredictable nature of prime numbers. While mathematicians have strong evidence that the pattern should hold, a complete proof is still missing. This problem is important because it connects to the broader question of how prime numbers are distributed among whole numbers. Prime numbers appear to become less frequent as numbers grow larger, but they never disappear completely. If Legendre's conjecture is true, it would confirm that prime numbers always appear regularly, no matter how far out into the number system we go. Many attempts have been made to prove this conjecture, but so far, no one has succeeded. It remains one of the great mysteries of number theory. If solved, it could provide deeper insights into the behavior of prime numbers and their patterns. Until then, Legendre's conjecture remains an open problem, waiting for someone to finally prove whether it is always true or if an exception exists somewhere in the infinite sea of numbers. 15. The Hadwiger-Nelson problem. How many colors do you need to color a plane? The Hadwiger-Nelson problem is a fascinating question in mathematics that deals with coloring a plane while following a simple rule. The question is, what is the minimum number of colors required to color an infinite flat surface so that no 2 points exactly 1 unit apart share the same color? This problem was first introduced by Edward Nelson in 1950, but its origins can be traced back to work done by Hugo Hadwiger earlier in the 1940s. The challenge seems simple, yet even after decades of research, mathematicians have not been able to find the exact answer. To understand the problem, imagine drawing a large collection of points on a flat surface, connecting all pairs of points that are exactly 1 unit apart with a line. The goal is to assign colors to these points in such a way that no 2 connected points have the same color. The key question is, How many different colors are needed to guarantee that this rule is never broken? Early attempts at solving the problem suggested that at least 4 colors were needed, but no one could prove whether fewer colors might be enough. Later, it was discovered that no solution with fewer than 4 colors is possible. In 2018, mathematicians made progress by proving that at least 5 colors are needed, but they were still unable to determine whether 6 or 7 might be necessary. This means that the answer lies somewhere between 5 and 7, but the exact minimum number remains unknown. The Hadwiger-Nelson problem is important because it belongs to an area of mathematics known as graph theory, which has applications in computer science, telecommunications, and scheduling problems. Understanding how to efficiently color a plane without conflicts could have practical implications in areas such as wireless network design, where different frequencies must be assigned to avoid interference. Despite the progress made, the problem remains unsolved. Mathematicians continue to search for a final answer, using both traditional mathematical techniques and computational approaches. Whether the true answer is 5, 6, or 7, solving the Hadwiger-Nelson problem would mark a major breakthrough in graph theory and combinatorial mathematics. Until then, the mystery of how to properly color an infinite plane remains open. 16. The Polignac conjecture. How often do prime gaps repeat? The Polignac conjecture is a deep and unsolved problem in number theory that concerns the gaps between prime numbers. It was proposed in 1846 by the French mathematician Alphonse de Polignac, and it states that for every even number, there are infinitely many pairs of prime numbers that differ by that number. To understand this, consider the concept of twin primes, pairs of prime numbers that differ by 2, such as 3 and 5, or 11 and 13. The twin prime conjecture, which we discussed earlier, is a special case of Polignac's conjecture, where the gap is specifically 2. However, Polignac's conjecture extends this idea further, suggesting that prime pairs also appear infinitely often with larger even gaps. For example, if the conjecture is true, there should be infinitely many pairs of primes that differ by 4, such as the pairs 7 and 11, or 103 and 107. There should be infinitely many pairs of primes that differ by 6, such as the pairs 5 and 11, or 11 and 17. This pattern should continue for all even numbers, no matter how large. While mathematicians strongly believe this conjecture is true, proving it has remained an enormous challenge. One reason is that prime numbers become less frequent as numbers get larger, making it increasingly difficult to track these prime gaps. There has been significant progress in recent years. In 2013, the mathematician Yitong Zhang made a groundbreaking discovery, proving that there are infinitely many prime pairs with a gap of at most 70 million. Later improvements by other researchers reduced this gap significantly, getting closer to 2. However, no one has yet proven that every even number has an infinite number of prime gaps, as Polignac predicted. If proven true, the Polignac's conjecture would provide deeper insights into the distribution of prime numbers, one of the most mysterious areas of mathematics. It would confirm that prime numbers, despite their irregular spacing, follow a hidden structure that persists indefinitely. For now, the conjecture remains unproven. Whether mathematicians will eventually find a final proof, or if some even numbers do not have infinite prime gaps, remains an open question. 17. The ABC conjecture, a deep mystery in number theory. The ABC conjecture is one of the most important and mysterious unsolved problems in modern mathematics. It was first proposed in 1985 by the mathematicians David Masser and Joseph Oesterle, and it suggests a surprising relationship between 3 numbers, A, B, and C, that are linked by simple addition and multiplication. The conjecture states that if A and B are 2 whole numbers with no common factors, and their sum is C, then there is a limit to how many distinct small prime factors the numbers A, B, and C can have. In simpler terms, the more repeated small factors these numbers have, the less likely their sum will be related in a predictable way. This may sound abstract, but if proven true, the ABC conjecture would have profound consequences for number theory. Many famous results, including Fermat's last theorem, could be derived as simple consequences of this conjecture. In fact, if it were solved, it would automatically provide proofs for dozens of previously difficult problems in mathematics. In 2012, the Japanese mathematician Shinichi Mochizuki claimed to have proven the conjecture using a highly advanced mathematical framework known as interuniversal Teichmüller theory. However, his proof is so complex that more than a decade later, most mathematicians have still not been able to fully verify or understand it. Some experts believe the proof may be correct but incomplete, while others remain skeptical. The ABC conjecture is significant because it describes a hidden structure within numbers, linking addition and multiplication in a way never seen before. It could lead to new breakthroughs in understanding the distribution of prime numbers and their role in fundamental equations. For now, the problem remains open. Until Mochizuki's proof is fully verified or a completely different proof emerges, the ABC conjecture continues to stand as one of the greatest mysteries in modern mathematics. If solved, it would reshape entire areas of number theory and provide a new perspective on how numbers behave. 18. The minimum Ramsey number. Mystery: how big must a group be to guarantee order? The minimum Ramsey number problem is one of the most famous unsolved questions in combinatorics, a branch of mathematics that studies how objects can be arranged. It asks a surprisingly simple, yet incredibly deep question. How large does a group need to be to guarantee a certain level of structure? The problem comes from Ramsey theory, which deals with the idea that in any large enough system, some kind of order must eventually emerge. The classic example is a party where every person either knows or does not know another person. The Ramsey number tells us the minimum number of people needed in the party to guarantee that there will always be a group of people who either all know each other or all do not know each other. For smaller groups, the answer is known. If there are only a few people, randomness can still exist, and there may not be a predictable pattern. But as the number of people increases, order must emerge. The problem is that for larger groups, no one knows the exact number where this transition happens. The Ramsey number represents this tipping point, but its exact value is unknown for most cases. Despite being easy to describe, Ramsey numbers are incredibly difficult to compute. The numbers grow exponentially, making them impossible to determine by brute force. For example, while we know the Ramsey number for a group of 3 or 4 people, the exact number for a group of just 7 remains unproven. In fact, mathematicians only have rough upper and lower estimates for larger cases. This problem has real-world applications in computer science, network theory, and even biology, where understanding how structure emerges in large systems is crucial. If mathematicians could determine Ramsey numbers exactly, it would provide insights into how patterns develop in complex systems, from social networks to molecular structures. For now, the minimum Ramsey number remains one of the biggest open problems in combinatorics. Mathematicians continue to search for a general formula, but until then, the exact point where randomness must give way to order remains a mystery. 19. The lonely runner. Conjecture: can a runner ever be truly alone? The lonely runner conjecture is a famous unsolved problem in number theory and combinatorics that deals with movement and timing. It asks a seemingly simple question. If several runners start at the same point but move at different speeds around a circular track, will there always be a moment when one of them is alone, meaning that no other runner is nearby? Imagine multiple runners starting at the same location on a circular track. Each runner moves at a constant but different speed. As time passes, the runners spread out. The conjecture states that, no matter how many runners there are, Each one will eventually find a moment when they are far enough away from all the others to be considered alone on the track. This problem was first proposed in 1967 by the mathematician Jörg Wils, and it has fascinated mathematicians ever since. Despite extensive testing and partial proofs for small numbers of runners, no one has been able to prove that it is always true for any number of runners. One reason the problem is so difficult is that it combines elements of number theory, geometry, and motion, making it hard to analyze mathematically. Even though the behavior of a few runners can be calculated and verified, as the number of runners increases, the complexity of their movement patterns makes a general proof elusive. The lonely runner conjecture is more than just a mathematical curiosity. It has applications in scheduling problems, signal processing, and even astronomy, where understanding how objects move at different speeds in a shared space is crucial. While many mathematicians strongly believe the conjecture is true, a full proof remains one of the great open problems in combinatorial mathematics. Until someone finds a general proof, the question remains, can every runner eventually have a moment alone? Or is there some rare case where a runner is never truly alone? The answer is still unknown. Next, ChatGPT said, 20. The Rado's billiard ball problem. Will a bouncing ball ever repeat its path? The Rado's billiard ball problem is a fascinating unsolved question in dynamical systems and geometry. It asks, if a billiard ball is hit on a perfectly smooth, frictionless table, will it eventually return to its starting point and repeat its path forever? In an idealized billiard table with no friction, a ball will continue moving indefinitely. If the table has no pockets and the ball bounces perfectly off the walls, the movement follows strict mathematical rules. The key question is whether there are some shapes of tables where the ball's motion becomes completely predictable and eventually cycles back to where it started, repeating the same path forever. For some simple table shapes, such as a perfect square or rectangle, the behavior is well understood. In these cases, depending on the starting position and direction, the ball may either move in a predictable pattern or cover the entire table evenly. However, when the table is shaped like a polygon with angles greater than 90 degrees or has curved boundaries, the motion of the ball becomes much harder to predict. In certain cases, the ball's path appears to be completely chaotic, never repeating and never settling into a predictable loop. Mathematicians want to determine whether there exists a general rule that can predict when the ball will cycle back to its original trajectory and when it will not. This problem is related to ergodic theory, which studies the behavior of systems that evolve over time. It also has applications in physics, optics, and even planetary motion, where objects move without friction and bounce off surfaces in space. Understanding these patterns could help scientists predict the long-term behavior of celestial bodies or even optimize certain engineering designs. Despite its deceptively simple setup, the Rado's billiard ball problem remains unsolved. Mathematicians continue to explore whether a universal rule exists for predicting motion in these systems. Until a proof is found, the question remains open. Can we always determine if a billiard ball will repeat its path, or will some motions remain unpredictable forever? 21. The large gaps between primes. Problem: how far apart can prime numbers get? Prime numbers are the building blocks of arithmetic, but their spacing remains one of the biggest mysteries in number theory. The large gaps between primes problem asks a simple yet profound question. How large can the gap between consecutive prime numbers become? We know that prime numbers become less frequent as numbers grow larger, but their distribution appears unpredictable. Sometimes, primes appear close together, like 11 and 13. Other times, they seem to spread out, leaving large gaps between them. The question is whether these gaps have an upper limit or if they can continue growing indefinitely. Mathematicians have known for centuries that prime gaps increase as numbers grow, but the precise nature of this growth is unknown. In the 1930s, the mathematician Paul Erdos showed that there exist arbitrarily large gaps between prime numbers, meaning that no matter how far along the number line we go, we can always find prime numbers that are extremely far apart. However, Erdos's result did not provide an exact formula for how these gaps behave or grow. A major breakthrough came in 2014 when the mathematician Yitang Zhang proved that there are infinitely many pairs of prime numbers that are separated by, at most, 70 million. This was later improved by other mathematicians, bringing the gap down significantly, but the full picture of prime gaps remains unknown. Understanding the behavior of large prime gaps is crucial for number theory and has connections to the Riemann hypothesis, another major unsolved problem. Prime gaps are also important in cryptography, as prime numbers form the basis of modern encryption methods. Despite centuries of research, no one has been able to prove an exact rule governing how prime gaps grow as numbers increase. The ultimate question remains unanswered. Can we precisely predict how prime numbers are spaced, or will their distribution always remain a mystery? Until a definitive proof is found, the nature of large gaps between primes remains an open problem in mathematics. 22. The structure of random graphs. Is there an order in chaos? The structure of random graphs is a deep and unsolved question in graph theory, a field of mathematics that studies networks and connections. The problem asks, if we randomly connect points with lines, will a hidden structure always emerge, or can a graph remain truly chaotic? A graph is a mathematical structure made up of points, called vertices, connected by lines, called edges. Graphs are used in a wide range of applications, including social networks, computer science, and biology. Some graphs are carefully designed with clear patterns, but in a random graph, the edges are placed without any predefined order. The mystery is whether patterns still appear even when randomness is involved. This problem was first explored by the mathematicians Paul Erdos and Alfred Renyi in the 20th century. They introduced the idea of random graphs, where edges are added between points at random. Through their research, they discovered that as a random graph grows, certain patterns tend to emerge, almost as if the randomness itself follows hidden rules. For example, when a graph is small, it looks chaotic, but as more edges are added, large connected structures begin to appear. At some point, a critical threshold is reached where order seems to emerge from the randomness. The problem is that no one has been able to prove exactly when and how this transition happens in a general case. Understanding the structure of random graphs is crucial for network science, data analysis, and artificial intelligence. It helps researchers study everything from the spread of diseases to how information moves through social networks. If we could predict when a random system will become structured, it would have wide-reaching applications in technology and science. Despite many partial results, the full picture remains unclear. The fundamental question, does every large enough random graph contain a predictable structure, remains unanswered. Until mathematicians find a complete proof, the mystery of order in randomness continues to challenge our understanding of complex systems. 23. The existence of certain hyperbolic knots. Do special knots follow hidden rules? The study of knots is an important part of topology, the branch of mathematics that explores shapes and spaces. A knot, in mathematical terms, is a closed loop that does not intersect itself. While knots may seem like a simple concept, they can be incredibly complex, and one of the biggest mysteries in the field is whether certain types of knots, known as hyperbolic knots, always follow hidden mathematical patterns. A hyperbolic knot is a type of knot that can be studied using hyperbolic geometry, a non-Euclidean form of geometry where space curves in unusual ways. Mathematicians have found that most knots are hyperbolic, meaning that they can be understood using the principles of hyperbolic space. However, despite decades of research, no one has been able to determine exactly which knots will always be hyperbolic and which ones will not. The key question is whether there is a clear mathematical rule that determines whether a given knot can be classified as hyperbolic. Some knots, like the trefoil knot, have been extensively studied and their properties are well understood. But for more complicated knots, the rules that determine hyperbolicity are not yet fully known. Understanding hyperbolic knots is important for more than just pure mathematics. Knots appear in physics, chemistry, and even biology. The structure of DNA, for example, often involves knotted forms, and certain chemical molecules take on knotted shapes. If mathematicians could fully classify hyperbolic knots, it could lead to advances in understanding how molecules behave and how materials can be designed at a microscopic level. Despite much progress, the full classification of hyperbolic knots remains unsolved. Mathematicians continue to search for patterns and structures that could reveal a hidden order among knots, but until a general rule is found, the mystery of hyperbolic knots remains an open problem. 24. The ergodic theory of the circle. Will every point be visited? The ergodic theory of the circle is an unsolved problem in dynamical systems and number theory that explores how points move around a circle when rotated by a fixed amount. The central question is, if you keep rotating a point on a circle by an irrational amount, will it eventually get arbitrarily close to every possible position, or will some points never be reached? To understand the problem, imagine starting with a point on a circular track. Instead of moving in one full lap each time, you rotate the point by a fixed fraction of the circle. If this fraction is a rational number, such as 1/2 or 1/3 of a full circle, then after a certain number of steps, the point will land exactly where it started, repeating the same positions forever. But if the rotation is by an irrational number, such as the golden ratio or the square root of 2, the point will never return to exactly the same position. Instead, it seems to spread across the circle unpredictably. The big question is whether, given enough time, the point will eventually come arbitrarily close to every position on the circle. In mathematical terms, this asks whether the sequence of rotations is dense, meaning that for any position on the circle, no matter how small the gap, there will always be a point that gets close enough. This problem is important in physics, engineering, and chaos theory, as it relates to how systems evolve over time and whether their behavior can be predicted. It has applications in quantum mechanics, planetary motion, and even music theory, where understanding periodicity and randomness plays a crucial role. Mathematicians strongly believe that the answer is yes, that an irrational rotation will always lead to dense coverage of the circle. However, proving this rigorously for all irrational numbers remains an unsolved challenge. Until a definitive proof is found, the question remains, will a point rotated by an irrational amount truly explore the entire circle, or are there gaps that will never be filled? 25. The extension of the Kakeya needle problem. Can a needle turn in zero space? The Kakeya needle problem is a famous question in geometry that asks whether it is possible to rotate a needle in place using as little area as possible. The problem was first posed by the Japanese mathematician Soichi Kakeya in 1917, and since then, it has led to deep mathematical discoveries. However, a major unsolved extension of the problem remains. Can the total space required for rotation be made arbitrarily small, approaching zero? To understand the problem, imagine a thin, rigid needle lying flat on a surface. The goal is to turn it completely around so that it points in the opposite direction. In the most obvious case, the needle can simply rotate inside a circular disc with the same length as the needle. However, the question becomes more interesting when we try to minimize the area needed for rotation. Kakeya originally asked if it was possible to rotate the needle within a triangular-shaped region of minimal size. The answer turned out to be yes. A special type of triangle, now known as a Kakeya set, allows the needle to turn while occupying a surprisingly small area. However, mathematicians later discovered even more exotic shapes, known as Kakeya needle sets, that allow rotation in arbitrarily small regions. This led to the shocking possibility that a needle might be able to turn in a space that approaches zero area. The major unsolved extension of the problem is whether there exists a true zero-area Kakeya set in higher dimensions. If such a set exists, it would mean that rotation is possible with virtually no space at all. This has huge implications for analysis, physics, and signal processing, where similar principles are used to understand how waves and motion behave in confined spaces. The problem is closely connected to harmonic analysis and fractal geometry, two fields of mathematics that study infinitely complex patterns. Some researchers suspect that the key to solving the problem may involve fractals, which can be infinitely detailed yet occupy zero measurable space. Despite its seemingly simple origins, the Kakeya needle problem remains one of the great unsolved mysteries of mathematics. Whether a true zero-area solution exists or whether some fundamental limit prevents it is still unknown. Until a final proof is found, the question of whether a needle can turn in an infinitely small space remains unanswered. 26. The gaps between consecutive Fibonacci primes. Is there a pattern? The Fibonacci sequence is one of the most famous number sequences in mathematics. It begins with the numbers 1 and 1, and each new term is the sum of the two previous ones. This produces the sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. Some numbers in the Fibonacci sequence are also prime numbers, meaning they can only be divided by 1 and themselves. These are called Fibonacci primes, and they include numbers like 2, 3, 5, 13, and 89. The mystery is, do Fibonacci primes follow a hidden pattern, and do the gaps between them grow forever? At first, Fibonacci primes appear frequently, but as the sequence grows, they become less common. The gaps between them seem to increase, but mathematicians do not know for sure whether these gaps always get larger or if prime numbers continue appearing at somewhat regular intervals. The central question is whether there are infinitely many Fibonacci primes, or if they eventually stop appearing altogether. No one has been able to prove whether Fibonacci primes go on forever, or if the gaps between them will grow so large that no more will ever appear. Some mathematicians suspect that there may be a final Fibonacci prime, meaning the sequence would eventually contain only composite numbers. However, no proof exists for this idea. This problem is important because it combines two fundamental areas of number theory: the Fibonacci sequence and prime numbers. Both play a major role in cryptography, computer algorithms, and mathematical modeling. Understanding whether Fibonacci primes are infinite could reveal deep connections between number sequences and prime distributions. Despite extensive computer searches, no one has been able to fully explain the pattern of Fibonacci primes. The question remains, do Fibonacci primes continue forever, or will there come a point where no more exist? Until a proof is found, the mystery of their spacing and existence remains one of the great unanswered questions in mathematics. 27. The optimal network layout problem. What is the most efficient way to connect points? The optimal network layout problem is an unsolved question in graph theory and optimization that asks, what is the best way to connect a set of points using the shortest possible total length of connections? This problem appears in many real-world scenarios, such as designing transportation networks, electrical grids, and internet infrastructure. The goal is to minimize costs and maximize efficiency by finding the shortest and most effective way to connect multiple locations. One version of this problem is known as the Steiner tree problem, which asks for the shortest network that connects a given set of points. Unlike a simple direct connection between all points, the optimal solution may involve adding extra connection points, called Steiner points, to reduce the total length of the network. Finding the absolute best solution, however, is incredibly difficult as the number of points increases. Mathematicians have been able to solve this problem for small numbers of points, but for larger networks, finding the perfect solution is computationally impossible using current methods. In fact, the general form of this problem is known to be NP-hard, meaning that no efficient algorithm is known to exist that can always find the best solution in a reasonable amount of time. This problem is critical for many industries. In telecommunications, it affects how internet cables and cell towers are placed to provide the best coverage with the lowest cost. In logistics, it impacts how delivery routes are designed to minimize travel distance. In biology, it helps researchers understand how veins in plants and blood vessels in the body form efficient networks. Despite its importance, the optimal network layout problem remains unsolved in its general form. Mathematicians and computer scientists continue to develop better approximation methods, but a universal formula or efficient algorithm that works for all cases is still unknown. The central mystery remains: is there a mathematical shortcut to finding the most efficient way to connect points? Or is this problem fundamentally unsolvable for large networks? Until a breakthrough is found, the best possible network layout remains an open question in mathematics and optimization. 28. The packing density of spheres in higher dimensions. How efficiently can we stack spheres? The packing density of spheres. Problem is a fundamental question in geometry and higher dimensional mathematics. It asks, what is the most efficient way to pack spheres together in different dimensions? In three-dimensional space, the best way to stack spheres, such as oranges in a grocery store, is known as the Kepler conjecture. This states that the most efficient packing arrangement is the hexagonal close packing or face-centered cubic packing, which fills about 74% of the available space. This was proven in 1998 with the help of computer-assisted calculations. However, in higher dimensions, the problem becomes much more complicated. In 4, 5, or more dimensions, the best way to pack spheres is still unknown for many cases. Mathematicians have discovered certain efficient packings in some dimensions, but there is no general formula that works for all cases. One of the most surprising breakthroughs came in 8 and 24 dimensions, where mathematicians discovered that spheres could be packed in an unexpectedly perfect arrangement. These discoveries were made using lattice structures and had connections to deep mathematical areas such as coding theory and number theory. In these dimensions, the best packing methods were found to be optimal, meaning no denser arrangement is possible. However, in most other dimensions, the problem remains open. This problem is not just an abstract mathematical puzzle. It has real-world applications in areas such as data compression, error-correcting codes, and quantum computing. Understanding sphere packing helps with signal transmission, digital storage, and even optimizing how atoms arrange themselves in materials. Despite progress in some special cases, mathematicians still do not know the most efficient way to pack spheres in many higher dimensions. The big question remains: is there a universal rule that determines the best way to stack spheres in any dimension, or does each case require a unique solution? Until a final proof is found, the mystery of sphere packing remains an open problem in mathematics. 29. The sum of square roots. Problem: can we always tell when a sum of square roots is a whole number? The sum of square roots problem is an unsolved question in algebra and computational mathematics that asks, given a sum of square roots of whole numbers, can we always determine whether the result is a whole number? To understand the problem, imagine adding together several square roots, such as the square root of 2 plus the square root of 8, the square root of 3 plus the square root of 12. In some cases, these sums simplify to whole numbers, but in other cases, they do not. The question is whether there is a general mathematical rule or algorithm that can always determine whether a given sum of square roots simplifies to a whole number. This might sound like a simple problem, but no one has found an efficient way to solve it in all cases. While basic algebra can simplify some sums of square roots, as the number of terms grows, the calculations become increasingly complex. The difficulty lies in determining when terms will cancel out perfectly to produce a whole number. This problem has important implications in computer science and symbolic computation, where algorithms must decide whether certain calculations can be simplified. If a general rule were found, it could improve how computers handle equation solving, geometric computations, and mathematical proofs. Mathematicians suspect that an efficient algorithm should exist, but no one has been able to prove or disprove its existence. The key question remains, can we always determine whether a sum of square roots equals a whole number, or are there cases where the answer is unknowable? Until this mystery is solved, the sum of square roots problem remains one of the great open questions in algebra. 30. The perfect rectangle problem. Can a square be divided into unique rectangles? The perfect rectangle problem is an unsolved question in geometry that asks, is it always possible to divide a square into a set of rectangles, each with different dimensions, so that no two are the same size? This problem is a variation of the perfect squaring problem, which asks whether a square can be divided into smaller squares, all with different sizes. Mathematicians have proven that such a division is possible, and these patterns are called perfect squared squares. However, when we replace squares with rectangles, the answer remains unknown. To solve the problem, we must find a way to break a square into rectangles of different sizes, ensuring that no two rectangles share the same dimensions. So far, no one has been able to prove whether a perfect rectangle tiling is always possible, or if some squares cannot be divided in this way. This problem is important in tiling theory and combinatorial geometry, with applications in architecture, materials, science, and computer graphics. If mathematicians can prove whether a perfect rectangle tiling always exists, it could lead to new discoveries in how shapes can be arranged efficiently. Despite efforts by researchers, no general solution has been found. The big question remains, can every square be divided into unique rectangles, or do some squares resist this kind of tiling? Until a proof is found, the perfect rectangle problem remains an open question in mathematics. 31. The odd weird number. Problem. Do odd weird numbers exist? A weird number is a special kind of number in mathematics. A number is considered weird if it meets two conditions. The sum of its proper divisors, all of its divisors except itself, is greater than the number itself. However, no subset of those divisors adds up exactly to the number. For example, the number 70 is weird because its divisors are 1, 2, 5, 7, 10, 14, and 35. When added together, these sum to 74, which is greater than 70. However, no combination of these numbers adds up to exactly 70, making it a weird number. So far, all known weird numbers are even. The question that remains unanswered is, do any odd weird numbers exist? Mathematicians have searched extensively for odd weird numbers but have never found one. Some believe that they may not exist at all, meaning that weird numbers might be exclusive to even numbers. However, no one has been able to prove that odd weird numbers are impossible. This problem is important in number theory, where understanding how numbers interact with their divisors helps in cryptography, algorithms, and the study of perfect and abundant numbers. A proof showing that odd weird numbers do not exist would deepen our understanding of how divisors behave. For now, the mystery remains. Is there an odd number that meets the conditions of a weird number? Or are all weird numbers forever even? Until a proof is found, the search for the first odd weird number continues. 32. The prime quadratic sequence problem. How long can a pattern keep producing only prime numbers? The prime quadratic sequence problem is a mystery in number theory that explores how long a specific mathematical pattern can keep generating only prime numbers before eventually producing a number that is not prime. Some special patterns have been discovered that generate long sequences of prime numbers when whole numbers are used as input. One of the most famous examples continues to create prime numbers for the first 40 steps before eventually producing a non-prime number. Other patterns have been found that last for even longer, but so far, all known cases eventually stop producing only primes. The big question is whether there exists a pattern that never fails, one that can generate an endless sequence of prime numbers without ever producing a composite number. While many mathematicians believe that such a pattern is impossible, no one has been able to prove this for certain. This problem is important because prime numbers play a key role in encryption, computer security, and cryptography. If a mathematical pattern could be found that reliably generates prime numbers for an extremely long time, it could revolutionize the way prime numbers are used in digital systems. Despite extensive research, the answer remains unknown. The question stands, is there a perfect pattern that will always produce prime numbers, or must every sequence eventually fail? Until a definitive proof is found, the mystery of the prime quadratic sequence remains one of the great unanswered questions in mathematics. 33. The eternal Sudoku problem. Can every Sudoku puzzle be solved with logic alone? The eternal Sudoku problem is an unsolved question in combinatorics and puzzle theory that asks, can every valid Sudoku puzzle be solved using logic alone, or are there some puzzles that require guessing? Sudoku is a well-known number puzzle where a grid must be filled with numbers following specific rules. A properly designed Sudoku puzzle should have a unique solution, meaning there is only one way to complete the grid correctly. However, some Sudoku puzzles seem to require trial and error rather than pure logical reasoning to reach the solution. Mathematicians want to determine whether there exists a Sudoku puzzle that is logically unsolvable, meaning that at some point, a player must make a guess because no logical deduction can be made. So far, no one has been able to prove whether such a puzzle exists. This problem is important in game theory and artificial intelligence, as solving Sudoku efficiently is closely related to how computers approach logical problem solving. If a puzzle requiring guessing were found, it could mean that some logic-based problems have fundamental limits where reasoning alone is not enough. Despite extensive testing, no one has found a definitive answer. The question remains, is there a Sudoku puzzle that logic alone cannot solve, or is every possible puzzle logically solvable? Until a proof is found, the mystery of the eternal Sudoku problem remains open. 34. The Erdos-Strauss conjecture. Can every fraction be split into three parts? The Erdos-Strauss conjecture is an unsolved problem in number theory that asks whether a specific fraction can always be written as the sum of three smaller fractions. Despite being simple to state, it has remained unproven for more than 70 years. The conjecture focuses on the fraction known as 4 over n, where n is any whole number greater than 1. The question is whether this fraction can always be rewritten as the sum of three distinct fractions, each with a numerator of 1. In other words, is it possible to break down this fraction into three parts in a way that always works, no matter what value n takes? This idea comes from a long history of studying Egyptian fractions, which are sums of fractions where the numerator is always 1. The ancient Egyptians used this system because they did not have a standard way of writing fractions like modern mathematics. Instead, they expressed all fractions as sums of unit fractions, which means that every fraction was broken down into a series of numbers where the numerator was always 1. The Erdos-Strauss conjecture builds on this idea by asking whether a specific type of fraction, 4 divided by a whole number, can always be written in this way, using exactly three terms. For small values of n, mathematicians have found many examples where this breakdown works. For instance, when n is equal to 5, the fraction 4/5 can be rewritten as 1/2 plus 1/4 plus 1/20. When n is equal to 7, the fraction 4/7 can be rewritten as 1/3 plus 1/11 plus 1/231. However, proving that this rule works for every value of n has proven to be extremely difficult. Mathematicians have tested the conjecture for extremely large numbers, using computers to check billions of cases, and no counterexample has been found. However, proving that a pattern works in all cases is much harder than simply testing individual numbers. The challenge is that as numbers grow larger, the possible ways to break down the fraction become more complex, making it difficult to find a general rule that applies to every possible value. This problem is important in pure mathematics, particularly in the study of number theory and fraction decomposition. Understanding how numbers can be broken into sums of simpler fractions has connections to algebra, computer science, and even cryptography, where breaking down complex structures into simpler parts is a key challenge. Despite decades of research, no mathematician has been able to prove or disprove the conjecture. If a proof were found, it would confirm that this simple rule holds for all numbers. If a counterexample were discovered, it would mean that some values of n do not allow for this type of fraction breakdown. Until a solution is found, the Erdos-Strauss conjecture remains one of the great mysteries in number theory, challenging mathematicians to unlock the hidden patterns in fractions. 35. The square peg problem. Can every curve be fitted with a perfect square? The square peg problem is a long-standing unsolved question in geometry that asks, can every continuous curve that forms a closed loop contain 4 points that form a perfect square? Despite being easy to understand, this problem has remained unsolved for over a century. The problem was first proposed by the German mathematician Otto Toeplitz in 1911. The idea is simple. If you take any smooth, closed curve, like a stretched-out oval or a wobbly, irregular shape, can you always find 4 points along its edge that form the corners of a perfect square? For circles, the answer is obviously yes. A square can be placed inside a circle in many different ways. For shapes like ellipses and rectangles, mathematicians have shown that at least one square can always be found along the boundary. However, for more complex, irregular, or jagged shapes, the question becomes much harder. Mathematicians have been able to prove the result for some types of curves, such as those that are smooth or convex, meaning they do not have sharp corners. However, the problem remains open for all possible curves, especially those that might be highly irregular, with sharp bends or self-intersections. If a single example of a closed curve is found that does not contain a square, the conjecture would be disproven. But so far, no such example has been discovered. The square peg problem is related to a larger field of mathematics known as topology, which studies the properties of shapes that remain unchanged under continuous transformations. The problem is also connected to knot theory and computational geometry, fields that have applications in physics, biology, and even robotics. For example, understanding how shapes can be manipulated in space is important for designing robotic arms, analyzing DNA structures, and optimizing materials in engineering. In recent years, mathematicians have used computer simulations to search for counterexamples or patterns in how squares appear in different shapes. Some results suggest that squares may always exist in certain types of curves, but a complete proof has remained out of reach. If the square peg problem is solved, it would provide new insights into symmetry, geometry, and the nature of closed curves. If it turns out that all closed curves must contain a square, it would confirm a deep and unexpected link between randomness and geometric order. If a counterexample is found, it would challenge long-standing assumptions about how shapes behave in mathematical spaces. For now, the question remains unanswered. Does every loop contain a hidden square? Or is there some strange shape that defies this rule? Until a complete proof is found, the square peg problem remains one of the most intriguing and deceptively simple mysteries in mathematics. 36. The perfect cuboid problem. Does a perfect three-dimensional box exist? The perfect cuboid problem is an unsolved mystery in geometry and number theory that asks, does there exist a rectangular box in which all edges, face diagonals, and the space diagonal are whole numbers? A cuboid is a three-dimensional shape with 6 rectangular faces, like a standard box. In a perfect cuboid, not only must all 3 edge lengths be whole numbers, but all 3 face diagonals, which cut across each rectangular face, and the space diagonal, which connects 2 opposite corners of the cuboid, must also be whole numbers. This problem is a natural extension of Pythagorean triples, which are sets of 3 whole numbers that satisfy the Pythagorean theorem. For example, the numbers 3, 4, and 5 form a Pythagorean triple, because 3 squared plus 4 squared equals 5 squared. In 2 dimensions, a perfect right triangle exists when all 3 sides are whole numbers. In 3 dimensions, mathematicians are looking for a similar perfect solution in the form of a cuboid. So far, no one has ever found a perfect cuboid. Many examples of almost perfect cuboids exist, where all edges and face diagonals are whole numbers, but the space diagonal is not. Despite extensive computer searches, no example of a truly perfect cuboid has been found, leading some to believe that it may be impossible. However, proving that something does not exist is much harder than proving that it does, so the question remains open. The perfect cuboid problem is closely related to other famous unsolved problems in Diophantine equations, which involve whole number solutions to algebraic equations. These equations are deeply connected to the nature of whole numbers and prime factors, making them an important part of number theory. If a perfect cuboid exists, finding it could lead to breakthroughs in our understanding of how whole numbers interact with geometric shapes. This problem also has connections to cryptography and computer science, where whole number relationships are used in encryption and coding systems. A deeper understanding of integer-based geometric relationships could help in areas such as error detection, network security, and even quantum computing. Many mathematicians believe that perfect cuboids do not exist, but no one has been able to prove this with certainty. If a proof were found that ruled out all possibilities, it would close one of the longest-standing questions in geometry. On the other hand, if someone were to discover an example of a perfect cuboid, it would be a major breakthrough, proving that whole numbers can form a perfect three-dimensional shape in ways never seen before. For now, the search continues. Does a perfect cuboid exist, hiding somewhere in the infinite sea of whole numbers? Or is this the kind of mathematical object that can never be found? Until a final answer is reached, the perfect cuboid problem remains one of the greatest unsolved mysteries in mathematics.